Welcome to the Deep Dive, where we crack open the latest research to reveal the surprising truths within. Today, we're tackling something pretty fundamental in AI, this mystery of why large language models, these incredibly powerful tools, often just stumble when they need to think outside their training box. It's this constant push and pull, isn't it, between the simple training methods we like to use and the real flexible intelligence we're actually aiming for?
Yeah, for ages, it's been this trade-off. You've got Supervised Fine-Tuning, SFT, which is, well, pretty easy to get going.
Right.
And then there's Reinforcement Learning, RL, which seems better at generalization, but it's complicated.
Meritoriously so.
But what if I told you there's a breakthrough, like literally a single line of code that flips SFT on its head, making it generalize better than even some of those complex RL methods?
That's exactly what this paper, Dynamic Fine-Tuning, digs into. It uncovers this hidden kind of problematic reward structure just hiding inside standard SFT.
And that explains why it often struggles to generalize. And then, they introduce this incredibly clever solution, DFT. It basically just neutralizes that flaw.
Okay, so quick summary for everyone. We think we've found SFT's Achilles heel. And the fix is surprisingly elegant. Dynamic fine-tuning, DFT.
That's the run.
So our mission today, we're going to unpack that hidden flaw in SFT, show you exactly how DFT fixes it.
And the results are, well, pretty remarkable.
Right. We'll share those results showing it can even beat complex RL. It's this amazing bridge, really, between deep theory and a super practical fix for building better LLMs. All right, so let's dive in properly. To really grasp why this DFT thing is such a big deal, we need to get clear on the starting point. Supervised fine-tuning, SFT, what is it fundamentally?
Okay, SFT. Think of it like teaching someone by just showing them finished examples, like a master painter showing an apprentice only the final painting.
Right, no in-between steps.
Exactly. The apprentice just tries to copy the final product, exactly.
Right.
So for LLMs, that means you feed the model a bunch of input-output pairs, the expert demonstrations.
But questions and perfect answers.
Precisely.
Yeah.
And the model's entire goal is just to mimic those outputs. Make its own output look exactly like the experts.
That makes sense. And it sounds, well, pretty effective on the face of it, which is why SFT is everywhere, right? It's relatively easy to set up.
So straightforward, yeah.
And models learn fast. They quickly start producing things that look like the examples.
They acquire those expert-like behaviors rapidly.
But, and this is the big but we always hear, it struggles with generalization.
That's a consistent critique.
It's like that apprentice can copy the master's painting perfectly, but ask them to paint something new, even slightly different, and they're lost.
Exactly. There was that great line in another paper, SFT memorizes while RL generalizes. SFT is fantastic for replicating things it's already seen, but step outside that, even a little bit, and it often falls apart.
Okay, so that naturally leads us to reinforcement learning, RL. Why is it generally seen as better for generalization? Is it just about getting different kinds of feedback?
Pretty much. RL changes the whole learning game. Instead of just copy this exactly, the model gets reward signals based on how good its actions are.
More like quality feedback.
Right. Think of the painting apprentice again. Now, instead of just seeing the final piece, they get told, hey, that brush stroke is good, or maybe try a different color there.
Okay, actual guidance.
Exactly. It gets rewarded for trying things, for exploring. This allows it to discover new strategies, find solutions the expert maybe didn't demonstrate explicitly, and adapt better to new situations. It learns the principles, not just the examples.
That makes total sense for generalization, but here we go, the classic RL problem.
Yeah.
It's not easy, is it?
Definitely not a free lunch. It's computationally very expensive.
Right.
It can be incredibly sensitive to hyperparameters. Getting all those settings just right is tricky.
A lot of fiddling.
A lot of fiddling. And critically, you need those explicit reward signals. You need a way to tell the model good job or bad job.
Which isn't always obvious or even possible for many real-world tasks.
And this is where the new paper makes a really fascinating connection. They did a deep mathematical dive.
Okay.
And showed that the way SFT updates itself, its gradient update, can actually be seen as a special case of an RL method called policy gradient.
Whoa, wait, so SFT has a kind of RL mechanism hidden inside it already?
In a way, yes. It's like they found this implicit RL process running under the hood of standard SFT.
Okay, mind blown a little.
Okay.
But if it's there, what's the problem? What did they find that was so bad about this implicit reward in SFT?
Okay, here's the catch. This implicit reward, it's deeply flawed. First, it's incredibly sparse.
Sparse, meaning?
Meaning it almost never happens. Imagine training that coffee robot, but it only gets a reward, any reward, if the coffee is 100.00% perfect. Temperature, volume, everything.
Anything else gets nothing.
Zero feedback. That's basically how SFT's implicit reward works. It's only non-zero if the model's output token exactly matches the expert's token. One tiny difference. Nothing.
That sounds like a terrible way to learn, all or nothing. But you mentioned another issue, something about inverse proportionality.
Yes, and this is the real killer. That sparse reward is also weighted inversely by how likely the model thought that correct action was.
Say that again? Weighted inversely.
Yeah, mathematically, the reward signal gets multiplied by 1 divided by the probability the model assigned to the correct token, 1 pool.
Okay, so if the model was really unsure about the right answer but happened to guess it correctly?
Exactly. If pool was tiny, then 1 pool becomes enormous. That single lucky guess gets a massive reward signal, way out of proportion. And this causes chaos. They call it unbounded variance. The feedback signals are wildly inconsistent. It creates a pathological optimization landscape.
You've got to walk on ground that's constantly having earthquakes.
Precisely. The model gets whipsawed around, overreacting massively to these rare high-reward moments, especially those it was uncertain about. It leads to overfitting on those specific rare instances.
Oh, okay, I see it now.
That's the root cause identified in the paper for why SFT struggles with stability and generalization. It's learning from this incredibly noisy, spiky, unreliable signal.
Wow. Okay, so SFT was basically trying to learn in a hurricane because its internal reward system was fundamentally broken. That sets the stage perfectly for the solution. Dynamic fine-tuning, DFT. How does it fix this mess?
And the beauty is it's so direct. DFT targets that broken reward mechanism head-on. It dynamically adjusts the standard SFT learning objective.
Wow.
It multiplies the SFT update signal by the actual probability the model assigned to that correct token.
Wait, that's the one-line code change thing? Just multiply by the probability?
That's essentially it. It seems almost too simple, doesn't it?
It really does. How can that small change fix such a fundamental issue?
Because it perfectly cancels out the problem. Remember, the bad part was the weighting by 1 over the probability.
Right, the inverse part.
By multiplying by the probability, you effectively cancel that term out. The part in the numerator cancels the part in the denominator. Boom.
Okay.
So that unstable probability-dependent gradient estimator, it becomes stable and uniformly weighted. The earthquakes stop. The ground becomes solid and flat.
Okay, uniformly weighted. What does that mean for the learning process? What's the effect?
The really cool consequence is that the effective reward for DFT becomes a constant 1 for every single expert trajectory.
Always 1.
Always 1 if it matches the expert path. It's like saying, yes, that sequence was correct, with the same level of positive feedback every time, regardless of how confident the model was initially.
So no more overreacting to lucky guesses.
Exactly. It stops the model from obsessing over specific, low-probability tokens it happened to get right. The updates become more stable, learning is more consistent, and generalization improves dramatically.
And you don't need extra reward models or anything.
Nope. No extra sampling, no complex reward functions. Just modify the SFT objective itself. It's incredibly efficient. It's like telling the coffee robot, yep, good coffee, consistently for every good cup, promoting reliable learning.
Okay, the theory sounds elegant, almost beautiful in its simplicity, but did it actually work? Let's talk about the experiments. They tested this, right? Especially in those tough math reasoning tasks.
Oh yeah, they put it through its paces. First, in the standard SFT setup, they took strong base models like Qwen 2.5 math, LAM-A3, DeepSeek math.
State-of-the-art stuff.
Right, and fine-tuned them on Numina Math Coty, a dataset focused on complex, chain-of-thought math problems. Then they tested on really hard benchmarks, Olympiad Bench, AME, AMC, stuff that really requires reasoning.
And the results, were they just okay, or?
They were seriously impressive. Take Qwen 2.5 math 1.5b. With standard SFT, it improved a bit over the base model, like plus 2 points on average.
Modest gain.
With DFT, the average gain was almost plus 16 points.
16. Wow.
Yeah, nearly 6 times the improvement of standard SFT. And this wasn't a fluke. They saw similar large gains across different models and sizes. It just consistently delivered much better performance. But maybe even more telling was its robustness. There were cases, like on Olympiad Bench with that Qwen model, where standard SFT actually hurt performance. Made it worse than the base model.
Seriously, SFT made it dumber.
It happens. Overfitting can do that. But DFT, in that same scenario, boosted accuracy by over 11 points compared to the base.
That's huge.
It really highlights how much better DFT generalizes and how it avoids the pitfalls of standard SFT, especially on challenging out-of-distribution type problems. It doesn't break, it excels.
So better final scores, more robust. What about efficiency? Did it learn faster too?
Absolutely. They saw faster convergence. DFT often hit its peak performance way earlier in training, sometimes within just the first 120 steps.
Wow, that's quick.
Yeah, better early performance, higher sample efficiency. It learns faster and more effectively because it's not fighting that chaotic internal signal anymore. It's a smoother ride.
And they compared it to other methods too, not just plain SFT.
They did. They looked at importance-weighted SFT, IWSFT, which is a related idea. DFT generally came out on top.
And crucially,
DFT is simpler. IWSFT needs a separate reference model to calculate weights. DFT doesn't need that extra baggage, so it's often better and more efficient to run.
Okay, the SFT results alone are compelling. But then they took it into the offline RL arena. That feels like a whole different level of challenge.
Right. This is where you have pre-collected data, maybe with some positive and negative examples, but the model can't interact live. Usually you need complex RL algorithms here, like DPO, or even online ones like PPO, if you could run them.
And DFT.
DFT, adapted for this offline setting, achieved the best overall performance. It didn't just beat other offline methods like DPO and RFT.
Okay.
It actually outperformed strong online RL methods like PPO and GRPO on average across the math benchmarks.
Get out! It beat online RL from an offline setting.
That's what the results showed. For example, DFT averaged around 35.4 across benchmarks, while GRPO, a good online method, averaged 32.0.
That's kind of a big deal.
It really is. It suggests DFT could be a much simpler, more scalable way to get RL-like generalization benefits, especially when online interaction is expensive or just not feasible. You potentially bypass a lot of the complexity of traditional RL pipelines.
Okay, truly powerful results. Let's zoom in a bit on how it's changing the model. You mentioned that chaotic signal being smoothed out, but did they look inside the model's head, so to speak, like at token probabilities?
They did, and found something really interesting. Standard SST tends to just push up the probabilities of all tokens in the expert demonstration, trying to match everything equally.
Makes sense. It's trying to copy.
But DFT does something different. It has this polarizing effect. It strongly boosts the probability of some tokens,
The important one.
presumably, while actively suppressing the probability of others. You end up with this bimodal distribution. Lots of tokens the model is very sure about and lots it's very unsure about.
And which ones got suppressed?
Interestingly, it tended to be the grammatical glue. Words like the is let, punctuation marks. The scaffolding rather than the core concepts.
So what does that imply? Is the model learning to ignore the grammatical fluff and focus on the substance?
That's exactly what the paper suggests. For robust learning, maybe the model shouldn't try to be equally confident about every single token.
Right.
It might be better to deprioritize the grammatical stuff and really lock onto the core meaning, the key semantic content.
Which sounds remarkably like how humans learn, right? Focus on the concepts, not every single and or the.
It really does echo good learning strategies. Focus on what matters.
And this wasn't just some fluke of the settings, was it? They checked if it was sensitive to things like learning rate.
Yep, they ran ablation studies. DFT showed impressive robustness. Changing the learning rate or the batch size didn't break it. The benefits generally held up.
Okay, good.
It really indicates this is a fundamental improvement in the learning dynamics, not just finding a lucky sweet spot in the hyperparameters.
So amazing results, especially for math. But the authors themselves point out this isn't the final word, right? What are the next steps or limitations?
That's right, they're quite clear about that. The current work is mostly focused on mathematical reasoning datasets.
Makes sense.
And the models tested go up to about 7 billion parameters. So the big questions are, does this generalize?
And other tasks?
Exactly. They plan to test it on things like code generation, common sense reasoning, and also on much larger models, 13 billion parameters and beyond.
And even other kinds of data.
Yeah, they even mentioned exploring vision language tasks. The goal is to see if DFT is a truly general principle for improving fine-tuning across the board.
Okay, so we started this deep dive asking if SFT, the simple method, could be fixed to generalize like RL, the complex one. And the answer from this paper seems to be a pretty emphatic yes. Dynamic fine-tuning looks like a major step forward.
It really feels like a beautiful piece of work connecting theory and practice. They found the theoretical flaw, that wonky implicit reward in SFT, and devised This incredibly simple, practical fix, that one-line change that delivers huge gains in performance and generalization, even beating complex RL methods sometimes.
It's such a great reminder, isn't it? Sometimes the biggest leaps come not from just adding more complexity or data, but from really understanding the fundamentals and making a precise, elegant tweak.
So, thinking about the bigger picture, what could this mean? If teaching an LLM to focus on substance over grammatical filler works so well, what other human learning insights are we maybe missing in AI?
That's a great question.
And more broadly, could this idea of finding and fixing these unstable optimization landscapes with simple, theoretically grounded changes, could that unlock breakthroughs in other areas of AI too?
Definitely something to think about. Lots to mull over until our next deep dive.